Hello and welcome to lecture 25 of the course Theory of Computation. In this second chapter so far, we have seen context-free languages, and we have seen two ways to realize them: context-free grammars and Post-run automata. Right? And we saw that they are equivalent, and we saw examples for grammars as well as Post-run automata. In this section, which is the last section of this chapter, we are going to see pumping lemma for context-free languages. Okay, so there are lots of similarities with the pumping lemma for regular languages that we had seen at the end of chapter 1. Okay, so what is pumping lemma? It is a necessary condition for a language to be context-free. So just like the pumping lemma for regular languages was a necessary condition for a language to be regular, this is a necessary condition for a language to be context-free, right? And which means if a language is context free, the conditions of the pumping lemma has to be satisfied, and if we are able to show that the conditions of the pumping lemma are not satisfied, then we can infer that the language is not context free. So we can use pumping lemma to show that the languages are not context free, right? So you can use it to show languages are not context free. We cannot use it to show that languages are context free, right? So to show languages are context free, we need to construct a PDA or a CFG or something, but we can use pumping lemma to show that it is not context free, right? And once again, the names are same by Bar-Hillel. This was discovered by Bar-Hillel, Perles and Shamir in 61. In fact, in the pumping lemma for regular languages also was a special case of this, right? So this by the same people, right? So the structure of the statement of the pumping lemma and the way it is applied, all of these are very similar, right? So there are only some minor differences in the way the pumping lemma for context-free languages differs from pumping lemma for regular languages. Many things are very similar, so we'll highlight the differences. So even in the statement of pumping lemma itself and in the way we apply it. Okay, so let's see. So pumping lemma says that if a language A is a context-free language, then there is a pumping length P, such that if you take any string S in A whose length is at least P, right? S is of length at least P, then we can partition S into 5 parts U, V, X, Y, Z, such that the following 3 conditions are satisfied, right? So if A is a context-free language, there is a pumping length, and if you take any string in the language which is of length at least the pumping length, then you can partition that string into 5 parts U, V, X, Y, Z, meaning as a concatenation of these 5 strings, such that the following conditions are met. Condition 1 is that U, V power I, X, Y power I, Z is in A, right, for all I. Condition 2 is that Vy, okay, so Vy, not Vx or Xy, it is Vy. The length of Vy is strictly greater than 0. Okay, this means that both of them cannot have 0 length, or in other words, both of them cannot be empty strings. Either V has to be not an empty string, or Y has to be not an empty string. And finally, we have Vxy. The length of Vxy, which is the middle part, at most P. Okay, so these are the 3 conditions. So let's just contrast them with the conditions of pumping lemma for regular languages. In the case of regular languages, we had the partition S as U, V, W, right, where into 3 parts, not 5 parts. And condition 1 was that U, V power I, W is in A, right? This was condition 1 for all I. Condition 2 was that length of V was strictly greater than 0, meaning V was not an empty string. I don't recall if I used XYZ or UVW, but I'll just use UVW now. And condition 3 was that, I think I used XYZ, so maybe I'll just replace it with XYZ. Right? S is equal to XYZ. One was that X, Y power I, Z is in A. 2 was that the length of y is strictly greater than 0, meaning y is not empty. And 3 was that the length of xy is at most p. Right? The length of xy is less than or equal to p. These were the 3 conditions in the pumping lemma for regular languages. Maybe I'll just right. These were the 3 conditions. So instead of 5 pieces, we split into 3 pieces. First part was that x y power I z is in A for all I. So here it is 5 parts, and we have, just to contrast, we have, instead of x y power I z, we have u v power I x y power I z. So the second and the fourth parts are going to be repeated how many ever times as per the count of I. And here in regular languages we had y greater than or equal to 0, right? Or sorry, the length of y is strictly greater than 0. Here we are saying that vy is strictly greater than 0, meaning when we had y should be non-empty in regular languages, here we are saying either y or v should be not empty. And in regular languages we have length of xy was at most p. Here we have vxy was at most p. So there it was xy, which was the initial 2 parts. Here which is vxy, which is the middle 3 parts. So there are some similarity. The structure is certainly similar, but in the actual statement itself there are some small differences, right? So let's see why this is true, right? So in pumping lemma for regular languages, we use the finiteness of the DFA, right? So we said that A is regular, so there is a finite automata DFA for A, and then we said that if the length of the string is greater than the number of states, then it has to revisit some state, right? And this revisiting some state was turned out to be the middle part of the string. So now when you revisit a state, you can revisit it again and again and again. You can go through the same loop. This was the high level idea of the proof of pumping lemma for regular languages. Basically, if the length of the string is long enough, some state has to be revisited because you have only a finite number of states, and by using pigeonhole principle. In case of context-free languages, we use the finiteness of the context-free grammar. Okay, not the DFA, but not the PDA, but the finiteness of the grammar. Basically, the idea is this: if a string is long, then the rules we may have to like if the string is really long, we may have to apply the rules many times, right? Because every rule may have a limited number of limited length of string appearing in the right hand side. So if the string is long, we may have to apply the rules many times. So the derivation may be long, and in a long derivation, because you have only a fixed number of variables, some variable must come again. So some variable must repeat. And this is what we exploit to get the pumping lemma, right? So if the string is long, the derivation has to be long. And if the derivation, when I say derivation has to be long, I mean many steps. And if there are many steps, we cannot have all distinct variables because the number of variables is bounded. So some variable must come again. And this we will exploit to show that these conditions should be met. So in other words, suppose t is the starting variable, right? T is the starting variable and t derives s, okay? So s is in the language, so t must derive s, right? And what we mean is this. So at some stage, let's say you got some string like this, u r z, where r is some variable, okay? And u and z are some strings which consist of both variables and terminals, okay? So u and z could be both variables and or let's say u and z is entirely terminals, okay, and r is a variable. Then let's say because the string is long, this r yields vry again, okay, meaning this r yields vry. So which means that the r yields something that has an r again, right? So this is what I've written here. So if the string is long, the derivation has to be long. Some variable r must derive itself at some point, right? So that's what I'm written here. R derives V R Y, and now where and then the R derives. So initially R derives V R Y, and then the middle R derives X. Okay, so that's what is happening, and this is what we will exploit for the pumping lemma. Okay, so so basically the key point is this, the fact that R derives itself, right? So this is what we will use, right? So now one may ask, why not derive R? So we got VRY from R, but we could use that same thing again, right? So for instance, we can do this. So we said T gives URZ and R gives VRY, right? So the middle part R gives VRY, right? Now what if this R again gave VRY? So you have UV and UV before that, which is this one, and you have YZ after that. So this R is going to give this VRY. And we may do this again. So you have UVV at the beginning and YYZ at the end, and this middle R is going to give VRY. So we may use that rule. So if R is able to derive VRY as per the rules of the context-free grammar, we can apply it again and again. So this means I can get some string like UVVV X YYYZ, or I may be able to get something like let's say T URZ, right? So I can use instead of R I can put VRY, right? And instead of this R, right, the underlined R, I get VRY again, right? And now I am going to replace this R by X, right? So this is, we know that over here we know it is allowed, right? This R was replaced by X. So UVV X YYZ, right? Or I could do something else. I could do something like T gives URZ. This is one possible derivation, right? And now directly, instead of deriving VRY, I can derive X from R. So I could get UXZ. So notice that now by these three derivations, right? These three derivations, I got three strings. One is UVVV X YYYZ. Two is UVV X YYZ. Another one is UXZ. So these three strings. So what we are saying is that if some R derives itself, now I can the part V and Y, I could repeat it in the original string. V and Y repeated or came up just once, but I could have it 2 times or 3 times or even 0 times. That's what I'm saying here, right? So the three strings that we got here are so the strings that we got here are UXZ or UVVXYYZ or UVVVXYYYZ, right? And so on. So all of these strings can be derived from the starting variable as per the rules of the grammar. So all these strings may be derived from the CFG, right? So just because we know that R derives itself and R derives X, R derives VRY and R derives X, we can combine them in different ways to get these things. And that is pretty much the high level idea of the proof of the pumping lemma, right? So the only things that we need to formalize here is, I just said a hand wavy thing like if the string is long, the derivation is long, and then some variable must repeat. So once we kind of quantify these things, what do I mean by if the string is long, and what do I mean by the derivation is long, and how can we like conclusively say that some variable must derive itself, right? So these things, once we kind of formalize, the proof is there. That's the proof, right? So let's go to the formal proof. Let B be the maximum number of symbols on the right hand side of any rule. Okay. So so if you look at all the rules of the grammar, right? A gives XYZ, or A gives 0A1 or something. So look at the right hand side and see what is the length of the right hand side. How many symbols does it contain? When I say symbols, I am talking about both variables and terminals. So let us call it B, right? For instance, if it is a Chomsky normal form, we know that any rule, the right hand side has at most 2 variables or a single terminal, right? So that we know that B is 2. In case of a general context free grammar, I am just calling it B. Okay, so it could be 3, it could be 10, right? It doesn't matter. We just want a finite number, which we can define as per the grammar, because a grammar has a fixed number of rules. You go through all the rules and see which rule has a maximum number of symbols on the right hand side, and you call that B, right? And now let us note one thing, that if the height of the parse tree is h, right, this is what I want to say. If the height of the parse tree is h, is at most h, then the length of the derived string cannot be more than b power h. Okay, so if the height of the parse tree is h, at most h, then the length of the derived string is not more than b power h. So let's quickly see why. Right, so I'll just do it in the right hand side. Suppose b was 3, right? So in one step of the derivation, like from the starting variable, let's say t, I could get 3 different symbols, and then let's say some of them are terminals, some of them are variables. So the worst case, everyone is a variable. They can give rise to, let's say, 3 more variables, and this can keep going. And if the height is, let's say, h, right, at the end we will generate a string of length 3 power h, right? Because if you look at it after the first level, right, there are 3 symbols. If you look at the second level, there are 9 symbols. So every time it gets multiplied by 3, but it need not get multiplied by 3, but it may get multiplied by something smaller. But then we want to give an upper bound. So we said that the maximum number of variables or terminals on the right hand side is 3. It could be 2, it could be 1, but this is an upper bound. So that the worst case is every rule gives 3 variables or 3 terminals or whatever. So now we get 3 power h. So if the height is h, then the height of the parse tree is h, then the length of the string is at most 3 power h, right? If the height is, so in this case, every rule gives rise to at most 3 symbols on the right hand side. If it was now, instead of 3 it was b, then we would get b power h, right, which is what we said here, right? So now let's say the number of variables is given by cardinality of v, because v, capital V is in the set of variables. So this denotes the number of variables. Now the pumping length that we get is just b power v plus 1. So b power v plus 1, where the exponent is v plus 1. Okay, so it's b raised to v plus 1, not, and clearly this is at least b raised to v plus 1, right? Because here the 1 is in the exponent, here the 1 is outside. So b power v plus 1 is at least b power v plus 1, right? So this is the pumping length. The pumping length is b power v plus 1, where v plus 1 is the exponent. So any string of length, at least the pumping length, to derive that string, the height of the derivation tree must be at least v plus 1, right? So any string of length at least p, the parse tree has to be of height at least v plus 1. Okay, why is this? Because if the parse tree has height v or less, then the length of the string will be b power v or less. Right? That's what we said here. That's what we said here. If the height is at most h, then the length is b power h, at most b power h. So if the height is v or less, then the length of the string is b power v, at most b power v. But by the choice of the string, the length of the string is at least p, and we know that p is at least b power v plus 1. So the height of the parse tree has to be at least v plus 1, if not more, right? So now the height, so what do I mean by height of the tree? By height of the tree, what I mean is that you look at the tree, there is some path that is of length v plus 1 from the top of the tree to the leaf of the tree, from the root of the tree, which is the top, to the bottom of the tree, which is a leaf. So there is a path of length v plus 1, at least v plus 1, right? We know the height is at least v plus 1. So all the paths cannot, all the root to leaf paths cannot be of length less than v or less than or equal to v. There has to be at least one path, root leaf path of length at greater than or equal to v plus 1, right? So it has length greater than or equal to v plus 1 means that all through the paths, right? So all through the paths, so the top, at the top of the path, it is a starting variable t, right? Maybe you get other variables a, b, etc. But you notice that all these intermediate symbols are going to be variables, because if you get a terminal, let's say small a, then the small a cannot derive anything more, right? So it stops there. So we know that all the labels in this path are going to be variables, except for the last label, which will be some terminal, let's say a or something, right? Let's say something 0 or something, right? So in the path of length v plus 1, right, we have many all variables except, all the labels are variables except one, which is at the bottom. And when I have a path of length v plus 1, so let's say a path of length 3 looks like this, right? A path of length 3, right? This is length 3, and this has four vertices or 4 dots. So it may have t, a, b, and some symbol 0. So it has 3 variables and a terminal. So a path of length v plus 1 has similarly at least v plus 1 symbols, at least v plus 1 variables, and one terminal. So there are so I'll just erase this. So there are in this path of length height v plus 1, right? So this is height v plus 1. There are at least v plus 1 variables and one terminal, right? So there are v plus 1 variables and a terminal, and here I am saying the same thing. This has at least v plus 1 variables and a terminal, right? Okay, but we know that the grammar has only v variables, right? The v size of v by definition is the number of variables. So which means that some variable must appear, at least one variable should be there that appears more than once, right? And let r be that variable, right? So let pick r to be such a variable that appears more than once. And if there are multiple such variables, you look at the bottom, of the tree. From the bottom, you look at v plus 1 variables, right? Not from the top, from the bottom. And from the bottommost v plus 1 variables, you choose a variable that repeats. Okay. So there could be multiple variables that repeat, but you pick a variable that repeats in the bottom v plus 1 variables of that path. Okay. So this is the choice of the variable. This is how we choose r. So this is the key thing. Because the string is long, so again let me just say it once again. We took a string of length at least p, where p is b power v plus 1. Because the string is long, the height of the parse tree is at least v plus 1, and because the height of the parse tree is at least v plus 1, some variable is there that repeats, and let that variable be r. And if there are multiple such variables that repeat, you choose such a variable that repeats from the bottom bottom v plus 1 symbols. Okay, so this choice will matter in some aspect of the proof. Okay, so this is the picture that we have. We have the starting variable here, right? We have the starting variable t here. At some point r is derived. Okay, so when r is derived, the part to the left of r is u, okay, and the part to the right of r is z. So at some point, if you look at the derivation till this part, right, t gives u, r and z. But we know r derives itself again, and let's say r derives, now this r derives v r y. Maybe I'll highlight that. This r derives v r and y. Okay, so we say that this r derives v r y, and this r derives v r y, and the second r, maybe I'll use a different color highlight. I don't know if it's possible. Right, the second r, sorry, that not this. So the second r derives x. Okay, again this is a bit messy, so I'll just not use that color from now on. But the first r derives ry, and the second r derives x. So now the thing is that we could replace this gray triangle, right? We could replace this triangle. We could replace this triangle with a copy of this and this bigger triangle, because it is r that is deriving. R can derive v r y, right? So I could, instead of this gray triangle, I could replace this entire triangle, right? So then we get something like this. So where the gray triangle, this gray triangle is replaced by this entire copy of this triangle. So now if you see the derivation, the string that is derived is u v v x y y z. So u v v x y y z is derived. I could again do this again this small triangle can be replaced by this entire triangle. So I'll get v repeating 3 times and y repeating 3 times, u v v v x y y y z. Or I could even replace the bigger triangle with the smaller triangle, right? The bigger triangle, which gives where r gives v r y, I can replace with the gray triangle where r simply gives x. So then I get this. So in this case, the entire string is u x z, right? So the string here is, maybe I'll just write down here, string derived is u v x y z. Here string is u v v x y y z. So this is part of the same tree. Here string is u x z. So now you can see that I can v and y, how many ever times I want, I can repeat them. So the number of times v and y repeat is the number of times this particular triangle, right? Number of times we use the rule r gives v r y. So how many times we use this replacement rule, that is the number of times we get v and y repeat. So here we used r gives v r y once, and again r gives v r y, right? So we used 2 times. So you get u v v x y y z. In this case, we never use r gives v r y, so you don't have any v or y. So that's it. That's the proof of the first part of the pumping lemma, right? Which says that for each I, u v power I x y power I z is in the language, which is what we have shown for any. This is what we have shown. So for we can kind of divide the string in such a way and get v and y such that if you repeat v and y the same number of times, all those strings are in A. So just to kind of say what is v, what is x, what is y, etc. So we chose r to be the string that or the variable that repeats from the bottom. The first derivation of r, what comes before r is u and what comes after r is z. And when r derives itself, what comes before r, that is v, and what comes after r is y. And finally, when the second instance of r, what is derived by r is x. That's how we get u, v, x, y, z. So the first part of the first statement, that we can split s into u, v, x, y, z such that for all I, u, v power I, x, y power I, z is in A, is verified. And and now we have to show that vy is non-empty and vxy is at most p. So let's see why that is true. Suppose v and y were both empty, right? Suppose v and y were both empty. Then that means that this particular parse tree that we have, right? If v and y are both empty, then basically u, v, x, y, z is equal to u, x, z, right? If v and y are both empty, right? If v and y are both empty, then u, v, x, y, z is equal to u, x, z. So now, which means this parse tree that I have drawn here, right? This parse tree is a simpler way to derive the same string, right? This is a bigger parse tree because it has to allow r to derive itself and so on. So which means this is a smaller parse tree, but by our assumption, the parse tree that we chose was one that was the smallest. So the parse tree that we chose was one which had the smallest number of nodes. So if v and y are both empty, that contradicts the choice of the parse tree. Hence, v and y cannot be both empty. And now we have to show that vxy is of length at most the pumping length. Let's see why. And we chose r to be something that repeats. Okay, so this is by the choice of r. We chose r to be a variable that repeats in the lowest v plus 1 variables of the path. This means that out of the two repeating r's, right? So something happens, then some r, right? So something like this, right? X, y, z. Sorry, v, x, y. Sorry, right? V, x, y. The height of this entire tree is no more than v plus 1, right? We know that even in the v plus 1 variables there is some repeat. So we know that this height is at most v plus 1. This means that for any tree of height h, we already said this here, for any tree of height h, the length of the string is at most b power h, which means this means that r has height at most v plus 1. So length of vxy is at most b power v plus 1. And what is b power v plus 1? B power v plus 1 is nothing but our pumping length. So this is exactly what we want, which is the pumping length. Right. So by the choice of the r, we know that r is in the bottom v plus 1 nodes, and hence r gives vxy has height at most v plus 1, and hence vxy is of length at most b power v plus 1, which is the pumping length. So that is it. That completes the proof of the pumping lemma. So just to give the high level picture once again, if a variable is long, meaning longer than b power v plus 1, then the parse tree has to be of height greater than v plus 1, which means there has to be some path where some variable repeats. And now in that path, you choose the variable that repeats, and that tells us. So this picture is our is the one that guides the choice of the strings u, v, x, y, z. So from the starting variable and to the repeating variable, what is the string that comes before the repeating variable, that is u? What is the string that comes after the repeating variable, that is z? And now the repeating variable r derives itself. What is the part of the string that, so r derives some string, then r, then some other string. So the string that comes before is v and the string that comes after is y. So r derives v, r, y. And finally in the second repeating of r, what is the string that that is derived by r, that is x. And this defines the 5 strings u, v, x, y, and z, and the 3 conditions also we verified. And that is the proof of the pumping lemma. Once again, pumping lemma for context free languages is very similar to the pumping lemma for regular languages in the way it is stated and structured, and also in the way it is applied. Just that the difference in the conditions itself will be used while to get the proof or disproof that a language is not context free. But the way we argue, the structure of the proof, etc., is going to be very, very similar, right? And I think there is we have run enough time, and that completes the proof of statement and proof of the pumping lemma for context free languages. And we'll see some examples of this in action, in showing that some languages are not context free in the next lecture, which is lecture number 26. Thank you.